why don't we write out the balanced equation, and we're going to do an ice table underneath, right? So SO2 plus NO2 makes SO3 plus NO. If it didn't strike you immediately that this was a tougher problem, then I think as you start to fill out the ice table, you'll get a second chance to catch this fact. Is it clear we need an ice table to do this? It says all four gas had initial concentrations. Calculate the equilibrium concentrations. So when we're given the initial and then we're asked about something at equilibrium, we need to set up this table, right? The ice table to organize our information. On some level, this question starts off a little bit easier than the other ones because we've dealt with problems that tell us moles and volume, and we have to go find molarities. This question gave us molarities right off the bat, so it actually looks a little bit easier. 0.8 molarity, 0.8 molarity, 0.8 molarity, 0.8 molarity. Does that look unusual at this point? Here's where you get a second chance to recognize this is a tougher problem. What's unusual about this initial setup? And I don't mean the fact that there's 4 instead of 3 things in the equation, or that the number's 0.8 and we haven't seen a 0.8 before. What's different about this initial setup? Okay, they're all the same, yeah. Also, they could have been all different. That wouldn't matter. Evan?
We don't really know anything else about the change.
Now, yesterday we didn't know anything about the change or anything else, and so that was a clue we're going to use algebra, right? So this one's going to be an algebra problem. But do you remember yesterday when we did a problem like this, we said, okay, we're going to use x's, and we said this will lose 2x, this will gain 1x, right? These coefficients are all 1, 1, 1, 1. So I guess on the change line it's going to be x, 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 x. But where do I now have a problem?
You don't know which one's subtracting which one.
Exactly. I don't know, is it minus x, plus x? Or is it plus, plus, minus, minus? In other words, what I don't know is the direction that the reaction is going, right? If it's going forwards, it's going to be minus, minus, plus, plus. If it's going backwards, the left-hand things will increase, plus, plus, and the two product guys will decrease, minus, minus. So I don't know the direction that the reaction's going. How do I determine that? Yesterday, when we did problems, in fact, almost every problem we've done, we knew the direction because what was initially present on one side of the equation? On the initial line, in every question we've done so far, almost, the initial line had zeros in it, didn't it? So if the two products were not 0.8, but if they were zeros, then they would have to increase, wouldn't they? And then the left side would have to decrease. So what you might want to note here in your margin is that the problem here is there are no zeros on the initial line. Therefore, we don't know the direction the reaction is going. Okay? There are no zeros on the initial line of the ice table. And the reason that's a problem is because we don't know the direction the reaction shifts. So because there are no zeros initially, we don't know the direction. We don't know which way the reaction shifts. Anybody remember out there, gentlemen, you need to pay attention, please, okay? Anybody remember how we deal with not knowing the direction a reaction shifts? We've talked about this in the last couple of days. How do we determine whether a reaction shifts forwards or backwards?
Find Q.
we calculate the reaction quotient. We calculate Q. And Q is calculated the same way as K. So let's do that. I'm not going to do it underneath. I'm going to do it up here. Q is calculated the same way that we calculate K. So Q is going to equal the concentration of SO3 times the concentration of NO divided by the concentration of SO2 times the concentration of NO2. And I think you could probably do this in your head, right? These numbers are all the same. So what's Q going to equal if you put in 0.8 times 0.8 divided by 0.8 times 0.8? Q equals 1. How does that help me? Q is less than K. K was 3.75. Q is 1. So Q is less than K. And now we're remembering, well, yeah, we memorized this yesterday, hopefully. And the one we memorized yesterday said that if Q was bigger than K, we shift backwards. So if Q is less than K, we shift forwards. When Q is less than K, you shift to the right. With that understanding, go to your change line and put in your pluses and minuses. If we're shifting to the right, which side is going to increase? Which side is going to have pluses on it? It'll be the right side. So plus, plus. And the only way to get more products would be to lose reactants. And folks, that little bit that we just did right there, calculating Q because there were no zeros initially, so we could say which direction it was going, that's the only way that this problem is more difficult from yesterday's problem. This is what I meant by the hardest problem, but it's really just an extra little step. Okay? So let's finish it off based on what we did yesterday. This is going to be 0.8 minus x, 0.8 minus x, 0.8 plus x, 0.8 plus x. And at this point, I hope you're now sort of almost by reflex going ahead. At this point, we're going to set up the equilibrium expression with K, right? So 3.75, K is equal to 3.75 is equal to, I've already written out my expression for Q earlier, so I'm not going to write it again. I'm just going to substitute these things. It's going to equal 0.8 plus x. Now I could write times another 0.8 plus x, couldn't I? But since that's the same thing times itself, I'm just going to write 0.8 plus x squared divided by 0.8 minus x. And again, I could write times 0.8 minus x, or just 0.8 minus x squared. The reason it's nice to use squares is not just because you save ink, because now you look at it mathematically and you realize this is similar to the question we did yesterday. There's a squared on top and there's a squared on the bottom. How could I make the math much simpler? Squared on top, squared on bottom, you can square root both sides. So square root of 3.75, someone give me that on a calculator, please. Sorry? 1.93. Okay. 2 times 2 is 4. 1.93 times what? That kind of looks okay. Equals, what does square rooting do on the right? It gets rid of the squares. So we have 0.8 plus x over 0.8 minus x. Okay, and I hope you guys realize the chemistry right now is on hold, right? We're no longer doing chemistry. We're just doing some algebra, right? And in a minute, I'm going to review with you how to use your calculator solver feature, the graphing calculator, to do the same thing. Now you're going to multiply the 1.93 by the denominator, 0.8 minus x, and that's going to equal the numerator, 0.8 plus x. Okay? If you're wondering why that's true, just think about this, that 2 equals 8 divided by 4, so 2 times 4 has to give me 8. The same logic, 1.93 times the stuff on the bottom gives me the stuff on the top, right? So you grab your calculator, expand the stuff in the brackets, 1.93 times 0.8, 1.54 minus 1.93 times x equals 0.8 plus 1x. Now just bring your x's to one side, bring your numbers to the other side, and we'll be almost done. I'm going to bring my x's to the right, and I'm going to bring the numbers to the left. So I'm going to subtract 0.8 from both sides. 1.54 minus 0.8 gives me 0.74. And 1x plus 1.93 x's gives me 2.93 x's. And now I just divide by 2.93 on both sides. X equals 0.74 divided by 2.93 equals 0.25 molarity. Right? Let's, okay. So we're going to finish the problem. I'm just going to erase this crap here, make some space. So our answer for x was 0.25. Right? The question is asking us to find the concentrations of all gases at equilibrium. So since x was 0.25 molarity, we can say the concentration of the SO2 is equal to the concentration of the NO2, and they're both equal to 0.8 minus x, aren't they? .8 minus 0.25. 0.55 molarity. The two products, the SO3 is equal to the NO concentration, and they're both equal to 0.8 plus x. 0.8 plus 0.25, 1.05. And that's the end of that problem. Okay? Now you can check your answer. You can see right now if this is actually correct. Any ideas how? How do I know if those are the correct concentrations at equilibrium? Don't we know K? K was 3.75. So if I take 1.05, square it, and divide by 0.55 squared, in other words, if I put those concentrations back into the equilibrium expression, do I get 3.75 or pretty close to it? Realizing that there might be some rounding error, right? Okay. We'll stop here, and I'm going to show you how to use the calculator again, okay? Maybe we'll record that as well.